Section 4.3 is all about the greatest common divisor and the least common multiple. I'm going to let you try this example on your own. Let's go ahead and define the greatest common divisor. The GCD, or greatest common divisor, or sometimes you see it as the GCF, greatest common factor, of two whole numbers A and B, not both 0, is the greatest whole number that divides both A and B. So here's one way that you can illustrate the GCD to your students. You can buy these rods that represent different whole numbers. So we've got a 6 rod and an 8 rod. And when you want to use that to find the greatest common divisor of 6 and 8. So what we're going to do is find the longest rod that we can use multiples of it to build both the 6 and the 8 rod. So for example, if I pull out my 2 rods, I can build a 6 rod with 3 2 rods, or I can build the 8 rod with 4 2 rods. I could use the 3 rods to build the 6, but not the 8. We could use 4 to build the 8, but not the 6. 5 can't be used to build either, and the 6 rod could be used just to build the 6, but not the 8. So the greatest common divisor of 6 and 8 is 2. Let's look at the intersection of sets method for computing the greatest common divisor. So the idea here is that I'm going to take both of my numbers and list all of the whole number divisors of each number. Then I'm going to find the intersection, so there's my intersection of sets, and then I'm going to pick the greatest element in that set. So let's look at an example. I want to find the greatest common divisor of 20 and 32. So I'm going to start by listing the divisors of 20 and the divisors of 32, and I've denoted those with a D sub 20 and a D sub 32. So the divisors of 20 are 1, 2, 4, 5, 10, and 20. The divisors of 32 are 1, 2, 4, 8, 16, and 32. You can see I've drawn arrows between the numbers that match up, so that means my intersection of those two sets is 1, 2, and 4, and the GCD is the greatest number in that set. In this case, it's 4. So the GCD of 20 and 32 is 4. I'm going to let you try to find the GCD of 42 and 63 using the intersection of sets method. If you have trouble with that, please let me know. So that's our first method for calculating the GCD. Our second method is called the prime factorization method. So the idea here is that I'm going to write both of my numbers that I'm interested in their prime factorization form. And then the GCD is the product of the common factors, each raised to the lowest power of that prime that occurs in any of the prime factorizations. If we have numbers whose GCD is 1, we call those numbers relatively prime. So for example, 4 and 9 are both relatively prime. So let's try using the prime factorization method to calculate some GCDs. So the first thing I want to do is find the prime factorization of the two numbers here. So I want the GCD of 108 and 72. So 108 is divisible by 2. It's going to be 2 times 54. That's divisible by 2. That's going to be 2 times 27. 27 is divisible by 3. 3 times 9, and then I'm going to have a 3 and a 3. So 108 is 2 squared times 3 to the 4th. What about 72? 72 is 8 times 9. And I know that 8 is 2 cubed and 9 is 3 squared. So I'm not even going to write that out. I'm just going to say I have 2 cubed times 3 squared. So let me rewrite this as the GCD of 2 squared times 3 to the 4th and 2 cubed times 3 squared. Now what we're going to do is look for any common divisors in both of these prime factorizations. In this case, both have 2's and both have 3's. And so my GCD is going to look like 2 to the smallest power appearing in either of those factorizations In this case, that's going to be 2 squared times 3 to the smallest power appearing in either of those factorizations. I have a 3 to the 4th in the first one and a 3 squared in the second one, so I want 3 squared here. So 2 squared times 3 squared is 4 times 9, which gives me 36. All right, what about the GCD of 0 and 13? What's the greatest common divisor of 0 and 13? Well, 0 is just 0, and 13 is prime. What's the biggest number that divides both 0 and 13? It's 13. Right? 13 divides 13. 13 divided by 13 is 1. And 13 divides 0. 0 divided by 13 is 0. Let's look at some more examples. Let's find the GCD of x and y if x and y are as given in these problems. So here I've already given you the prime factorizations. So x is 2 cubed times 3 to the 5th times 7 to the 4th, and y is 2 times 3 to the 5th times 5 squared in part 1. So I'm going to look at those prime factorizations and identify any common primes. So they both have a 2 and they both have 3. And I'm just going to take each of those primes to the lowest power appearing in either factorization. So I'm going to have that the GCD of x and y here is going to be 2 to the 1st, that's the smallest power of 2 appearing, and times 3 to the 5th. And I'm just going to leave it in factored form here. What about number 2? X is 2 times 5 to the 4th times 11 times 13, and y is 7 squared times 3 times 17 squared. Both of these are already in their prime factored forms. And again, I just want to identify any primes that they have in common. In this case, we don't have any primes in common. So the GCD here, every number always has 1 as a factor or a divisor. And so the GCD of x and y here is just 1. That's the largest whole number that divides both x and y. All right, now I want to find the GCD of 3 numbers, and so there are a couple of ways that you could approach this. So if we've got them all in prime factored form, which I do, I want to identify the primes that are common to all 3 numbers. So here I have a 3 in the factorization of x, I have a 3 in the factorization of y, and a 3 in the factorization of z. And all 3 numbers also have 5s in their factorizations. And that's all that's common. So my GCD is going to be 3 to the smallest power of 3 appearing in any of those factorizations. In this case, it's 3 to the 1st in y, times 5 to the smallest power appearing in any of those factorizations. In this case, it's 5 to the 1st from x. Now you could have broken this down into 2 steps. So the GCD of x, y, and z is going to be equal to the GCD of of x and y together with z. So we could focus on the GCD of x and y first. In this case, I'm just looking at x and y. And here, the only primes they have in common are 3 and 5. The lowest power of 3 appearing in either factorization is 3 to the 1st, and the lowest power of 5 appearing in either factorization is 5 to the 1st. So the GCD of x and y is 3 times 5. And now I want to take the GCD of that with z. And if we look at z, z also has 3 and 5 as factors. And so the lowest power of 3 appearing between 3 times 5 and z is 3 to the first, and the lowest power of 5 appearing between the two is 5 to the first. In either case, I get a GCD of 15.